Hello everybody, let's continue our discussion of some concurrency theorems for triangles in Euclidean geometry. Okay, today we're going to discuss the excenter and ascribed circle. Okay, so let's see. We have a triangle PQR. Now it is not necessary that PQR should be an acute angle triangle. You can take a right angle triangle or what you call that, obtuse angle triangle as well. Same way of the same method of proof can be applied to those cases as well. Okay, all right. Let's see. We've extended the sides of the triangle PQR which meet at P. Okay, we've extended these sides and we've considered the external angle bisectors of Q and R. This is the internal angle. This is, so we call this, if we call the angles inside the triangles as internal angles, then that supplementary angles, this supplementary angle, when we extend, okay, 180 minus Q, this angle, this is what we call the external angle of this triangle at Q. Similarly at R, okay, we've considered the bisectors of the external angles at Q and R, which we have supposed to meet at E, okay, which we have supposed to meet at E. So yeah, now we are going to show first of all that PQ, QR and RP, okay, these three sides of the given triangle, they are equidistant from this point. All right, now let's draw a perpendicular. Let's draw a perpendicular. Let's draw a perpendicular. The distance between a point and a line is the length of the perpendicular from the given point to the given line. So if xy is the given line and P is the given point, and this is the perpendicular from P on xy, and let O be the foot of the perpendicular from P to xy, then the length of OP is what we call as the distance between the point P and the line xy. Okay, all right. Now let's see. Just like in the previous theorem, let's say this is EX, EY, and EZ. Okay, just like in the previous theorem, in triangles QXE and QZE, okay, QXE and QZE, a pair of angles, they're equal. A pair of angles, two pair of angles, now they're equal, and a pair of sides is equal. So this triangle is congruent to this triangle, as a result of which this is equal to this. Okay, corresponding sides of congruent triangles. Similarly, in triangles EZR and ERY, a pair of angles, they are equal. Two pairs of angles are equal. A side is common, so a pair of sides are equal. So these two triangles are congruent, as a result of which the corresponding sides are equal. So EZ is equal to EY. As simple as that. Now we're going to show that the internal angle bisector of P, we're going to show that we need to show that the internal angle bisector of P, internal angle bisector at P, passes through E, passes through E. Okay, passes through E. So just like in the previous case, let's, for the purpose of contradiction, let this not hold. Okay, you can correct my grammar if you want. Let this not hold means let the internal angle bisector of P or the internal angle bisector at P does not pass through E. Okay, we're assuming that, and now we're going to see that we are at a contradiction. Okay, and we do not need this part for the time being. Now let's join P and E. Okay, P and E, and let's see, just like in the previous case, in triangle PXE and PYE, they are right angle triangles. Number one, the hypotenuse of the two right angle triangles, they are equal, since this is a common side to both the triangles. Okay, and by our previous discussion, these two sides are equal. So in a right angle triangle, two pairs of sides in two right angle triangles, two pairs of sides, they are equal. This is equal to itself and this is equal to this. So these two triangles are congruent, as a result of which this angle is equal to this angle, means if this is theta, then this will be theta, as a result of which PE is a bisector of the angle at P, the internal angle at P. Okay, internal angle P. So PE is a bisector of angle QPR, but according to our assumption, it does not, the bisector does not pass through E, so this may be a bisector. So we conclude that angle P has two different bisectors. Okay, we have two different bisectors, so we arrive at a contradiction because an angle can have only one bisector. That's why we conclude that the internal angle bisector, we first conclude that this is wrong, so this is right. So internal angle bisector at P passes through the point E. Okay, now this point E is called the excenter of the triangle PQR with respect to P, because this excenter has been obtained by extending the line segments which form the triangle PQR and which meet at P. So since we have extended the line segments PQ and PR, okay, which meet at P, and this is and E is an excenter of this triangle corresponding to this, we say that, and that's why we say that the point E is the excenter of triangle PQR with respect to the point P. Similarly, we can have excenter with respect to Q and excenter with respect to R, and if there is let's say, it does not matter if one of the angles are right angle or greater than 90 degrees. Okay, the same process of proof can be applied to those cases as well. All right, so excenter is done. Now we were talking about EZ, these three lengths being equal, as a result of which we can draw a circle. With center at E and radius, let's say R, which would be something like this. Circle would look something like this. Not a bad circle. And this circle is called the ascribed circle. Okay, this circle is called the ascribed circle, or the X circle of the triangle PQR with respect to the vertex P. Okay, I hope that's clear, and thank you very much. Take care, everybody.